Welcome back, welcome back, welcome back. We're at question 5A of this 2020 paper, moving slowly but surely. And the question is on one of my favorite topics, logic gates. Now, those who know me know I love logic gates. I love them, I love them, I love them. And the question simply asks, complete table 2 by inserting the missing logic gates, symbols, and functions. Gates, symbols, and functions. So, it's 3 columns, 4 rows. So it's logic gate. The next column is symbol. And the final column is function, F-U-N-C. And here all we have is changes logic 0 to logic 1. This is our first row. Our second row has one word, and. Our third row has this word, or, and it has this symbol. Finally, the last row has NAND, N-A-N-D. And it just says produces logic 1 only when A and B are logic 0. Now, a logic gate is simply a digital device or circuit that gives you a known output for a given input. So basically, if you input specific conditions, you get a specific output. The output is not guesswork. If the input is a particular value, you know the output will be a certain value. Now, there are 5 logic gates that you need to know at this level 5. There is the NOT gate or the inverter. There is the AND gate, the OR gate, the NAND gate, and the NOR gate. NOT, AND, OR, NAND, and NOR. So, changes logic 0 to logic 1. This is the NOT gate or the inverter. You know what? Let me write my answers in a different color so that they're more easily seen. And I just love how the orange looks. So, NOT. The symbol for the NOT gate is this. A input, B output. The AND gate please forgive me for sinning. I drew this incorrectly. I drew this as an AND gate instead of an OR gate. I just realized that. The AND gate is the logic gate that has the straight, flat back. The OR gate is curved. That's the difference. This is A and B, your inputs, and that is your output. Now, this produces logic 1 when A and B are logic 1. The OR gate produces logic 1 when A or B are logic 1. And finally, the NAND gate is what we call an inverted AND. It's an AND gate, but the output is inverted, and we indicate the output being inverted by simply drawing a small circle at the output. So A, B. Now, let me just fix this so you don't think that this is an answer as well. This is curved. Good. So, NOT gate, symbol, AND gate, function. It produces logic 1 when A and B are, I kind of erased my E, are logic 1. OR gate produces logic 1 when A or B are logic 1. NAND gate that. An AND gate, but this circle means the output is inverted. And for this table, you get 1, 2, 3, 4, 5, 6 marks. Now, please remember there are 5 gates, not AND or NAND, and the NOR gate. Now, the NOR gate is the OR gate, but the output is inverted, and we indicate that by just drawing a little circle on the output. Here are your 6 marks. So, part B. With the aid of a circuit diagram, describe how an alternating current AC can be half-wave rectified to produce direct current across a resistor load. Now, once these people ask you, I called CSEC these people, may they forgive me. Once they ask you with the aid of a diagram, please note this is an opportunity to do well, because a well-drawn and well-labeled diagram makes explaining easy, very easy. I've always maintained and argued this. So, half-wave rectification. Now, while I clean the board, let me tell you what rectification is. Rectification is the process by which AC is converted into DC. Okay, now, for now I'll just clean it like this, so clean it properly a bit later. Alternating current is essentially current whose value is not constant with time, it varies, hence the name or the term alternating is applied to it. Direct current is current whose value remains constant or fixed over time. And rectification is the process by which AC is converted to DC. DC converted to AC is called inversion, but that's a different story altogether. So essentially what we're trying to do is convert an alternating waveform, time, into a direct current or DC waveform. Now, we're speaking specifically about half-wave rectification. So, this here, I love having multiple colors, it makes life fun. This here is one complete wave or cycle or oscillation. In half-wave rectification, we only get at the output, one of these, or one part, or one half of this wave. You say you get the top. What happens is the bottom is lost, the bottom half is lost. So you get a waveform that looks like, well, something is missing, okay? Because something is actually missing. Hence the term half-wave rectification. Now you convert this into that, and you might be thinking like, how do we do this? Well, we do this via means of a semiconductor diode. And the semiconductor diode is a unidirectional device that converts, or sorry, not converts, that basically just allows current to flow in one direction. So if this is our semiconductor diode, I know it looks just very close to a NOT gate, but it's not a NOT gate. And this is our AC input. We can take an output across the ends of, I was about to say the diode, but they said take it across a resistor, so I have to modify my circuit. I use the old symbol for resistor just for fun. Now, this is our input, and this will be our half-wave output. This is our circuit diagram. Now, what happens when we have an alternating current waveform is that in each half cycle or half wave, the current changes direction. So let's assume in the first half cycle, the current is traveling in this direction. Now, the diode conducts in the direction of the arrow. What happens is if current is traveling this way, current will pass through this diode, then pass through the resistor and head back to the source. But when the current direction is reversed and current decides to flow here, well, it can't travel in that direction. So that will account, or that will create this lost half cycle every time. Because current can only flow in that direction. When current changes direction, there will be no current flow. So this is the circuit that gives you, or that can be used rather, for half wave rectification. And they ask you to describe it. So the description, if you're looking for words, would be, since current is only allowed to flow in one direction, the diode will only conduct for one half cycle. And that half cycle will be indicated on or by the output. So you're either going to get the positive or upper half cycle, or the negative or lower half cycle. Depends on how you put your diode. And this would be your input again. This is your output. This is your simple circuit. I know I use the old symbol for resistor, but you could just draw that rectangular box instead. It will be fine. Just to recap, rectification is the process by which AC is converted to DC. There are two types of rectification. Half wave, which gives you this output, or full wave, which gives you the whole thing, including the missing portions. They wanted you to build a simple circuit to perform half wave rectification. Now you're going to have your source, your diode, which does the rectification, and your resistor, which is your load. So your output is taken across the ends of your load, and you will end up with a half wave waveform rather. And again, depending on how you put your diode, you're either going to get the positive or negative half cycles. And this was worth a total of 5 marks. 5 marks. The next part of the question actually asks for something I just gave. It says, and I will quote, sketch the VT graph to show the expected output across the load. VT is voltage time graph. Now, what you will find is that the output will look like this. And again, this is not the only correct answer. Depending on how you put the diode, the diagram could be inverted, and you could actually end up with the positive half cycle being lost and the negative half cycle being left. So you can get either one of these. This would be correct. Of course, this is time, and this is voltage. Time, voltage. So, simple circuit, output obtained. And that was worth a whole 1 mark. 6 and 6, 12. And I have one more part to work for you for 3 more marks, I believe. 1 second, let me get that. It says, and I'm reading again, draw a voltage time graph showing an AC source with frequency of 5 Hz and a peak voltage of 12 volts. Now you might be like, is this related to this question? No, it's not. It's not related to this part of the question, but it's important nonetheless. Now, they say draw a voltage time graph showing an AC source of frequency and peak voltage. Current waveforms are sinusoidal, meaning they look like a sine wave. Alright, they look like a sine wave. That being said, you can easily sketch one with little to no hassle. They give you frequency. You might be thinking, frequency? Yes, frequency. Now, every waveform has frequency, and frequency is equal to 1 upon period. You might be thinking, why is this important? If I ask you to sketch a graph, and I give you a grid, and I have time, of course, I will, in this case, I will have voltage in volts. how do you know where to draw the curves? You know it goes up and down like a sine wave, but when it comes to putting the numbers in, you need to know this formula. Now, if frequency is 1 upon period, period is 1 upon frequency. In this case, I almost wrote the answer. In this case, frequency is listed as 5 hertz. 5 hertz. What does that mean? The period or the time taken for one complete waveform is 1 upon 5, which is 0.2 seconds. What does that mean? It means from the start of the wave all the way to the end here is 0.2 seconds. The peak value of this waveform is given as 12 volts, meaning the maximum value it will achieve here and also the value here will be 12 volts. I didn't need to put the V in because it's on the y-axis and therefore voltage. So this is the waveform, and it simply said draw a VT graph showing an AC source with a frequency of 5 hertz and a peak voltage of 12 volts. Now, they gave you quite a lot of space on the paper, and if you're desirous, you could have filled in the rest. This would be 0.1, and if I drew this here, I know I'm drawing through my writing. This would be 0.4, this would be 0.3, and then it would be 0.5, 0.6, and so forth and so on. But peak voltage of 12 means the positive maximum and the negative minimum would be the same, 12. The time taken for one complete oscillation, this is a complete oscillation, is 0.2 seconds, and therefore the midway point is 0.1. And this is how you get your 3 marks, peak values and the correct period for the waveform. So we just finished our second question. Time to move on to question 4. Let me go grab it, clean the board, change my markers. I'll be right back. Welcome back. We're at question 4, and let us begin. Now, I read it already. Please don't think I memorized the paper. Question 4, part A says, with the aid of a diagram, state the 2 laws of refraction. With the aid of a diagram, state the 2 laws of refraction. Now, refraction is simply the process by which a ray of light bends as it passes from one medium to another. That's what happens, light bends. If you've ever stuck a pencil in a glass or tried to look at an aquarium from the side, you'd see that the objects, especially if you're looking at the aquarium not from the straight side but from the corner, you notice that the objects look a little weird in terms of where they're positioned. That's because light bends as it travels from air through glass and into water. 3 different media. But anyways, with the aid of a diagram. So, since we started with water, let us stick with water. If this is air and this is water, light will bend as it travels from air to water. So this is my ray of light. Now a ray is essentially a single thin beam of light, very, very thin. And then there is this little imaginary line. Let me draw it in with a black marker. It's called the normal. Now the normal is the line drawn at right angles to the point of incidence of a ray of light. Big words, I know. Essentially, you just draw the line at the point at which the ray of light passes from air to water. That's basically it. Incidence is just used to indicate where contact is made. So if something is incident on, it means it makes contact with or touches said surface. Now, this is your angle of incidence, or I hat. This is your angle of refraction, or R hat. The first law of refraction, first law, says the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for that boundary. It simply means if you find sine of this angle and divide it by sine of that angle, for any ray of light traveling from this water into this air, you're going to get a fixed or constant value. Now please note I said this water and this air. Alright, water generally has, I should say, a fixed refractive index, but experimental error and other conditions can cause that to vary ever so slightly. So this is the first law. The ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for that boundary. Now this is also known as Snell's law, S-N-E-L-L'(S), Snell's law. And simply sine I upon sine R is a constant called the refractive index. Any questions? Why did I ask any questions? Look at me asking any questions like if I'm in front of a class. I'm sorry, I just had to stand in front of the board flashback. This is the first time in a long while I've been in front of boards, so flashback. My bad, I'm sorry. The second law of refraction is, I'm going to say it and then write it. Now, if you notice, I drew the incident ray, the refracted ray, and the normal. The second law says that the incident ray, the refracted ray, and the normal all lie in the same plane. Incident ray, refracted ray, and normal all lie in the same plane. That simply means these three things rest on the same flat two-dimensional surface. We can see that here. If the normal was not in this plane, we would not see it. It would be at an angle to the plane. I shouldn't say we would not see it. We probably could, but it wouldn't look like it does now. These two are on the same plane, in other words, the same flat two-dimensional surface. They're essentially, it's like if you draw them on a sheet of paper, they can all fit on that flat sheet of paper, just like they can all fit on my whiteboard here. So, the second law is the normal, incident, and refracted, R-E-F-R-A-C-T-E-D, rays all lie on the same plane. And that's it. With the aid of a diagram, the two laws of refraction. And this was worth 4 marks. A whole 4 marks. All right. The second part of part A asks, when a diver under the sea, I read the words under the sea and I can hear Sebastian singing under the sea. Anyways, when a diver under the sea shines a beam of light towards the surface of the water, the light does not pass through the water air boundary into the air above, but reflects into the sea. State the name of the phenomena which occurs and briefly explain why. Now, the reason light is reflected at the boundary, again, diver in water, shines light, but the light doesn't escape the water, it bounces back down. It doesn't go through the boundary between water and air. And when it hits this boundary, it comes back down. This is called total internal reflection. Total internal reflection, TIR. TIR occurs when an angle known as the critical angle has been exceeded. Now, at the critical angle, this refracted ray no longer leaves, but travels along the boundary between water and air, or any two media. What happens is once this angle has been exceeded, once you go past the critical angle, the light will be reflected back into the water. This is TIR, and this is why it occurs. That was worth 2 marks. Now, continuing with our question, we are asked to do a minor calculation using this formula. Sin I upon sin R gives you the refractive index. Part B of the question says, another diver shines a beam of light into the water to see some fishes as shown in figure 2. Now, it says, given that the refractive index or the index of refraction rather, for the water is 1.33, and the angle of incidence I is 60 degrees. Calculate the angle of refraction R. Now, they give you the angle of incidence, they give you the index of refraction, and they're not asking you to find the angle of refraction. You just have to manipulate the formula. So if we rearrange, we get sine R is equal to sine I upon N. So this is the sine of 60 degrees upon 1.33. This is 0.866 over 1.33. That gives us 0.651. Point to note, whenever you're doing anything like this, please ensure your calculator is in degrees and not radians, please. So what we have is sine of the angle of refraction is equal to 0.651. Therefore, the angle of refraction is equal to sine inverse 0.651. By my calculations, .651 is 40.6 degrees. 40.6 degrees is our angle of refraction. Please note it is an angle, hence it is measured in degrees. Also do note that the refractive index is dimensionless, it has no units, so please don't ever put 1.33 degrees. Don't do that, just don't. Final part of the question, and it says, an object 2 cm in height is placed 10 cm in front of a converging lens with a focal length f of 6 centimeters. Calculate the image distance v. Calculate the image distance v. Now, this question, as pleasant as it is, involves a formula that does tend to prove to be somewhat difficult because of the fact that it has fractions. Yes, I said that. Proves to be difficult because it has fractions. Maybe like, why are you saying this? It's just true. Now, image distance v. Focal length, object distance, image distance. They said it's 2 cm high, 10 cm in front of a converging lens. 2 cm high, 10 cm in front of a converging lens with a focal length of 6 meters. Now, the 10 cm in front of the converging lens is object distance. The object is 10 centimeters from the lens. The lens's focal length is 6 centimeters. They want you to find this. So 1 upon 6 is equal to 1 upon 10 plus some unknown. Okay, well, I shouldn't even put some unknown. I'll just put 1 upon v. This implies that 1 upon 6 minus 1 upon 10 is 1 upon v. Let us just use 30. 6 into 35, 10 into 33. This is 2 upon 30. And this works out to 1 upon 15 equals to 1 upon v. Now please note, v is not 1 upon 15. 1 upon v is 1 upon 15. Therefore, v is 15 centimeters. This is the formula for focal length of a lens, involving object distance from the lens and image distance from the lens as well. You substitute, you transpose, you calculate, you get your answer. The answer is the image will be 15 centimeters from the lens, 15 centimeters. And again, I got 1 upon 15 is equal to 1 upon v. That does not mean v is 1 upon 15. That means v is 15 centimeters. And that brings us to the end of question Oh my. Look at me jumping the gun. That is not the end of question 4. One more thing. They ask you for the linear magnification of this lens. Alright, now, magnification is simply a ratio of image to object. Image height to object height, image distance to object distance. Now, they did mention that the object is 2 cm in height, which is not a problem. However, magnification, which is given by the formula M, let me just write here. All right, magnification is this, V upon U. Now, V in this case is 15, U is 10, that is 3 upon 2, or 1.5. The image is 1.5 times larger than the object. That is worth 2 marks. I'm sure 1 for the formula and 1 for the calculation. This was worth 4 marks. I'm sure 1 was for the formula, 1 was for substitution, 1 was for transposing, and the other was for calculating correctly, I'm sure. And probably, or maybe 1 of those marks could have gone to the answer instead. But lens formula, magnification formula. Magnification is always a ratio of image to object, not object to image. How much larger is the object, or how is the object compared to the image, not the other way around. So it's V, image, U, object. And that is the end of question 4. Now again, please check over all my calculations. You could leave comments under the video on Facebook. You're free to do so. I might read them and even respond. If you have questions, ask your physics teacher. I would say ask me, but I'm not sure how you're going to do that, but still, leave the questions and comments under the video. All will be read and accepted, and we'll try to respond. We genuinely will. If you have concerns or you need more clarity and you need more explanation, we do hope to give it to you in the future. We have more episodes coming, and in the meanwhile, stay safe, wear a mask, wash your hands, and I'll see you in the next episode. Peace.